Okay. Good afternoon. Many thanks for your time. So today there will be two parts to the session, and they're very fresh content, you will see. The first one is on segment routing traffic engineering. In fact, we've been shipping and deploying it for 18 months, gradually increasing the functionality. But we were so busy with the design and deployment that we took some delay in actually wrapping up a very good presentation on what is the architecture for SRTE. So just Saturday, a few days ago, I submitted to the ATF the main document for SRTE. And this is the first presentation that takes the whole architecture, and I'm going to walk you through that architecture. So it's really the first time you're going to see the complete architecture for SRTE. Then the second part is SRv6. In 2016, I spent almost most of my free time when not working with operators or on the ongoing product and design on SRv6. And so in this year, in calendar year 17, we're going to push forward on it. We'll have our first deployments, and you're going to see, I think it's going to be very big, very big. And so it's the first presentation on SRv6, public, completely, on really what we're going to do. In the past, these were very high-level presentation on SRv6. This time is going to be very clear, I think, on what are the use cases we are going after. Right after this session, there'll be my colleague José. So he's a key member of the team. He's working on some of the largest deployment in US on the SRTE. And so I reserve some time in my session or during the break, but it will only be 15 minutes for those who want to stay. But I encourage you to stay. He will do a demonstration of one of our flagship design and deployments for SRTE. It's something real. The code is there, shipping. We are under deployment at different accounts. So he can show you this, and I think it's very good to see this after the session. I want to ask, because through this, all the segment routing projects, the lead operators, the operators have played a key role in defining the technology. One of the aspects that I'm looking at right now is the need in the enterprise networks, campus, catalyst-based deployments. If you are interested in segment routing, if you think you have use case, if you have needs, etc., don't hesitate to ping me either after or over email, because I would really be interested to discuss with you, understand what is your use case, what is your constraints, your operating model, because I really need this data in order to think on how we're going to approach this. And I'm already working on it, but I would like to fine-tune a few things. Okay? Any question is welcome. Don't hesitate. And so let's go. So one slide on where we are with segment routing. It's a huge... my colleague in the back. We don't see it there. Fantastic. Thanks, José. Okay, so where we are with segment routing from an industry viewpoint. And it's really successful. We are really happy with it. So first, from an adoption viewpoint, we have reached everything we wanted to target. We have, at this time, 4 years after the first presentation on segment routing, we have deployments, real deployments, deployed, operated, in all the markets we were looking at. Web server, web provider, so the very large-scale web providers, service providers, and enterprise. Better than this, because you could think, it's always in the backbone. No. We have deployments in data center. We have deployments in the metro aggregation network. We have deployment in the backbone. We have deployments inter-domain. And so I think it's really fantastic in 4 years in terms of velocity. Everything we do is standardized. So our commitment to operators is very clear. There is not one bit of proprietary technology in segment routing. It has become the de facto IP-SDN architecture, that's clear. And we have worked very hard in order to get multi-vendor consensus. It's very important for the operators. If you want to stay up to date with the project, because we're still doing a lot of new things, and it will continue for a while, you can follow these different links. So we finally have released the book. So I think we worked a lot on this, so now it's there in printed version. So if you are interested, I think it's a very good reference. And then you have the segmentrouting.net website that we maintain that I think has been completely renewed and with lots of information. And then we maintain the LinkedIn, the Twitter, and the Facebook accounts updated with all the progress. That's the document that I mentioned. I released it on Saturday. That's the key reference for SRTE if you want to see its progress at the ATF. And you can see that this is co-authored with lots of providers in the industry, from Microsoft to Google to Deutsche Telekom. We've been working with quite influential operators on this topic. Okay, we go for SRTE. On your seat, I put a little mind map. It's because SRTE, you will see it's very, very powerful. So when we will do a training, when you'll see it on the website, you might get 400 slides. We would do a training for the whole day, etc. We could spend a day on it. I put the mind map because I think in one page, you get the key things. And so I think that in 40 minutes, I'm going to give you what is the most important. And so that mind map, I really recommend to keep it because I think it's a great summary to say, okay, that's the use case, that's what I can do, that's the automation. So while I'll go through the explanation, I will always explain the behavior with some CLI, some configuration, but remind that the key thing that I try to do when designing SRTE is to automate everything. And so first I explain with config, then I explain how to do it with on-demand generation of these, okay, on-demand instantiation. So RSVPT, this is where we started 4 years ago. Classic MPLS traffic engineering, very little deployment, many, many issues. It's not scalable, you know it well. It lays states in the core, that's very bad as an idea, but furthermore, it lays the state in k times n squared. So it's very unscalable. So there's no interdomain deployment and there's no interdomain applicability with RSVPT. Very complex configuration. These traffic engineering interface tunnel were very complex to configure. You had to configure a full mesh of them, a pain. Then complex steering with this notion of policy-based routing, auto-route, and again, all the configuration that you had to have. So that's where we started 4 years ago. And so for SRTE, I did it from scratch. And as you will see, I want everything from scratch. So we have our own process. We have zero dependency on the old MPLS RSVPT infrastructure. It's completely a new process. It's a completely new CLI. It's a completely new way to look at SRTE, okay? It's very important. We inherit nothing from the past. My goal was to have it simple, automated, and scalable. At the end of the presentation, I will end with this slide. So the challenge for you is to get convinced, or if you are not convinced, to tell me why, because then it's interesting for me to research on how to make it clear or to fix something that we might have forgotten. How am I going to achieve this? First, I remove the state in the core. This is given by segment routing. We put state in the packet header, not in the routers. So this is not a gain or a benefit of SRTE, that's a gain of segment routing in general. I need to do a bit more. I want to remove these tunnel interfaces because they were too complex and not performant. In segment routing, we're going to talk about a segment routing policy. So forget about this interface tunnel, they're gone. We talk about a policy that we're going to apply to packets. These policies, you don't want them to configure. And so very important to our technology is that these policies are going to be generated on demand. When you receive BGP traffic, VPN traffic, Lisp traffic, all of this traffic that goes to services, you're going to color them with the SLA they need. Low latency, disjointness, high bandwidth, etc. And it's the ingress P on the basis of the BGP route or the Lisp route that is going to on-demand trigger the policy associated with that color. You don't have to configure anything a priori. That's very important. And I'll reach to that point, and that will be the demo that José is going to show you. Furthermore, not only do you need to pre-configure all of this engineering path from A to B in a mesh, etc., but you don't have to configure the steering, which is a big gain, because remember how it was in the past. You had to maintain a full mesh of PE to PE of all of these tunnels, plus a full mesh of steering into this. All of this is gone. It's completely on demand, done by the router. So it's when a provider asked me this 3 years ago, initially I thought he was joking, because I said, how do you want us to do this? And it was a fantastic question, because by making the problem, we worked on it, and then actually it's not so complex. I wanted it to be multi-domain from scratch, because if we want to scale, we need to scale through multi-domain. And so you'll see we're going to cover this. This is the concept of XTC, our XR-based traffic engineering controller, and the notion of binding seed that are key to traffic engineering, and I would say to segment routing in general. You'll see that we have lots of functionality, and I said before, this is really the outcome of always working with the operators. So what you see is simply the outcome of the problem statement, the use case that the lead operators played. So as always, if you're interested in segment routing, if you have a nice idea or a nice use case, don't hesitate to contact me, because that's the fuel of the project. Okay, segment routing policy. As I explained it before, I'm going to explain with the CLI in the beginning, because I think that we have renewed, we have changed completely from zero, we have a new CLI. But at some point in time, we'll forget about the CLI, because we want to generate all of this on demand. I don't want you to configure this. But in order to gradually go through the technology, let me first explain how you would configure it. So first, we have segment routing. And we say we're going to do a traffic engineering, and we have a policy. And this is the name of the policy. So first, we have to identify it. The identification of a policy is going to be very important, because this is the key of all the automation. This is an endpoint and a caller. You already guess what it is. It is my BGP next stop and the caller of low latency, disjointness, high bandwidth. This is my Lisp locator and the caller. Okay? So this is why we define it this way. Then we have path. And when you have a policy, you might always have multiple options to realize it. Maybe you want to say to the router how to do it. Or maybe you want to say to the router what you want to achieve and let the router compute it. So there may be explicit path or dynamic path. And you might provide to the router multiple options for him to consider. And you want to maybe say one is more preferred than the other one. So in a policy, you'll have multiple paths. You show one here, then I can have multiple paths configured on the router, but very important, and you will see it over the course of the presentation and the use case, I might learn path for that policy, so this next stop and that caller. I might learn a path via BGP. I might learn a path via PSEP. I might learn a path via netconf. This is my interaction with the controller for the SDN use case. But I might have as well local path. The source of the path for a policy does not matter. The only thing that matters for the selection of the best path for the policy at a point in time is that the path must be valid and it has the best preference. Okay? So in this example, this is the most preferred one because it has the lowest preference. That path is an explicit one. This is a case where I say to the router, because maybe I have an offline planning tool, or I know it simply as a human being looking at the topology, I say to the router, I want you to use that label stack. And so all the packets, all the flows that will be steered in that policy, at that router, we will push this label stack on these packets. Okay? So it's an explicit path. But I might have as well dynamic path, where I don't want to be in the business of maintaining this label stack. I only want to say to my router, I want you to optimize based on the latency. This is a dynamic path. You must compute. I tell you what, minimize the latency, and I want you to execute the red links. And you will see later on everything that you can say to the router. Once you have expressed a path like this, the radar computes. On the basis of his traffic engineering database, he's going to compute the path that meets these criteria and express it as a label stack. And that will be the label stack that is pushed on the packet, if that path is the best one. In this example, it's not the best one because its preference is not the best preference at that time. But it may become the best if, for example, one of these labels go down. If, for example, the radar associated with this label go down, then this path becomes invalid, and the head end of the policy will select the next valid path with the next best preference. Okay? In the data plane, a policy is identified by a binding seed. It's a local label bound to the policy. In this case, we configure it explicitly and we give it the label value 1000. That's one option. Or you don't configure anything and you let the business to the radar, he will pick a local label and he will bind it to the policy. What is this role? This role is here. And this, the binding seed, is key because it's the ID in the data plane of the policy. Once the policy has selected its winning path, he installs it in the data plane, keyed by the incoming label that is the binding seed. And the outgoing action is to pop the incoming label and push the label stack of the winning path, the best path. We will steer on a policy in two ways. A remote radar might decide that he wants to go via me on a policy of me, and he doesn't want me to do the reclassification, the resteering, etc. He simply sends the packet with a label stack where there will be clearance followed by 1000. Clearance will get to me, clearance will be penultimate or popped, and when it comes to me, the 1000 is going to say to me, he wanted to go in that policy. I pop 1000 and I go into it. It's fantastic because this is the principle of segment routing. I put the state in the packet header, not in the network. Me in the middle of the network, or me in inter-domain application, I would have no way to reclassify that flow. It would be a pain to reclassify and maintain the state to say this flow needs to be there. No, it's better for the very ingress of the flow to maybe decide that you want to use a policy at me and encode it through the binding seed. So it's again an example that we encode state in the packet header, not in the fabric. This is an example of two policies at the head end one, and these two policies are going to the same endpoint, to the same BGP next hop. So they are both 4, but with a different color. And here you will make your choice. Me, I decided the color green means low latency, and the blue means high bandwidth. And so now I know that at 1, 4 green is the low latency path to go to 4. And 4 blue is the low latency path, is the high bandwidth path to go to 4. And so I have a binding seed for this one, and I have another binding seed for this one. And so the other way to steer, I already introduced what we will see later on, is that when I receive a BGP route where the next hop is 4, but the color is green, I simply install the BGP route in the data plane whose next hop is not 4. The next hop will be the binding seed of the green policy to 4. So it will be 1000, for example. And so from a data plane viewpoint, I see that BGP route that is indexing into directly on the policy. This is my automate steering. Okay, I lose no performance in this. You have to configure nothing, but also from a data plane viewpoint, from a PPS write, I am not losing any performance to do that steering. SRTE database. So I told you that we have a new process that is dedicated to SRTE that shares nothing with the old RSVPT process from MPLS Classic. In that process, we have our database. That database is built by design multi-domain. Any router running SR will have an SRTE database. Normally, in most of your deployments, they will be intra-domain. And so that database will be populated with the database of ISIS, OSPF, your IGP. But if you would want to run it multi-domain and let the router see the full multi-domain, it will be able to do. You simply need to feed it with the topology of the other domains, which you will do via BGPLS. Okay? So the SRTE is always multi-domain capable, but you might choose to only feed it with your local domain. This is again an example of what I said before. A given policy identified by the header at which it is applied, the endpoint and the color may have multiple paths. Some path may be of local config, some path may be learned via BGP, PSEP, or netconf. The source of the path does not matter. The only thing that matters is the validity. Here they are all valid, and I'll explain later on how we do the validity check, and then the preference. And the lowest preference wins. Okay? So at this point in time, there are 3 paths. They are all valid. This is 10. I prefer this one. If suddenly there's one of the labels used by that path, this is an explicit path provided by BGP. Let's say that the node number 3 goes down. So the label 16,003, the prefix label, the prefix seed 16,003 becomes unavailable into the topology. I invalidate this path immediately. So now that this path becomes invalid, the best path is this one, because it's the valid with the lowest preference. And in the data plane, I will install these seed lists, because each path could have multiple seed lists. Lots of functionality, but some of our operators wanted to have that capability. For most of you, you can think one path, one seed list. But we could do weighted ECMP as well. OK. Now I'm going to go into the dynamic path. So I'm in the section about you don't want to tell the router which labels he's going to use. You say to the router, low latency, disjoint path, plane affinity, and he computes. Okay? And first, I'm going to do it intra-domain. And then I will do it inter-domain. And first, I'm going to do intra-domain config, and then intra-domain automation. Then I will do inter-domain config to explain, and then automation. So first, you want to have native algorithm for segment routing. It's the same way. We have a new process because I wanted to have everything from scratch. We have a new CLI, but we have new algorithm as well. If you talk to someone that is trying to tell you to use the old RSVPT algorithm for SR, it is not good. And that's what I'm going to explain. So this is a topology that goes from 1 to, this is a topology. And I'm going to ask the router, please compute a path from 1 to 3, avoiding the red link. The old algorithms, the ATM frame relay RSVPTE algorithm, the circuit algorithm, this is what they are going to do. They prune the red links. Then they do a shortest path tree computation. They find the shortest path. They prune many paths because they are not able to express ECMP in circuits, so they take only one non-ECMP path along the shortest path tree. And so they select this one, and then they encode it as segments. And this leads to a segment list that is 4573. Bad. Why? Many segments. Poor ECMP. By design, it's a circuit algorithm. So if you reuse this algorithm for segment routing, it's better than nothing. That's clear, but that's not good. What is a true segment routing native algorithm doing? Same problem. The algorithm is going to compute that the best way to do this is the seed list 7-3. Because by going to 7, I have all the ECMP paths, and then I go to 3. And this is indeed the shortest path from 1 to 3, avoiding the red link. So this is much better because I need to push 2 labels instead of 4. But this is always also much better because I do load balancing. So this is what you should favor, and this is what we have in the implementation of SRTE. So let me give you an example. We call it the min metric with margin algorithm. And the research on this has been published as a scientific paper, accepted at SIGCOMM 2015, which is one of the best conferences from an IP academic viewpoint. So there was a lot of research behind this technology and behind these deployments. So we call it mean metric with margin. What is it? I'm at 1, and I may want to say to the router, I want you to find the path that minimizes the metric to 3. Which metric? It could be the IGP metric, it could be the TE metric, it could be the latency metric. Okay? Now, if I just say, in this example, I have each links have the IGP metric, which by default is 10, except here it's 30. And each links have the TE metric, which by default is 10, except here 5, 15, 15, and 8. So if I say to the router, I want you to find the path with the minimum TE metric from 1 to 3, it will find the green path. Because this is true. This is 5, 15, 23, while this is 25 and this is 30. It will find the lowest latency path. And this is going to tell you to that objective, is going to compute in this topology, this is 16,005 to go here, then 16,004 to go there, and then 16,003 to go there. Okay? Remember our convention, we always do this in my team, I'm very strict with this. Any label for illustration viewpoint, any label associated to a node is always 16,000 plus the ID of the node. We do this in the book, we do this in all our presentations. It's great, we can do this, and obviously we recompute every time the topology is changed, we would recompute and update the new path that meets that optimization. But you know that in a network, there may be paths that differ from each other with very little latency difference, or IGP metric difference, or TE metric difference. And so you may be a bit loose and say, I want to be on the low latency path within a margin of, let's say, 5 milliseconds, because then I would really like the ECMP it gives me, because I will distribute my traffic more. And this is what this algorithm can do as well. So here, this is my path, and I say it's dynamic, so I want you to compute. And I say minimize the T metric, I allow you a margin of 5, and I tell you, never use more than 6 labels. That's another thing that this algorithm supports. And so on the basis of this diagram, at this point in time, it would compute that the blue path, take the label 16,005, which is the prefix set of 5, and then take the label 16,003, which is the prefix set of 3. And this is indeed interesting, because now I'm doing more load balancing. I'm using less labels. So what this algorithm is doing is that it's allowing you to minimize on IGP metric, TE metric, latency metric, with or without a margin, with or without a limit on the maximum of labels you want to use. Okay? And there are different use cases depending on how you want to do this. It's not the only thing you can say the router you want to achieve. You can also express constraints. You might say to the router, I want you to have affinities that I want you to include in the path. So the red links, I want you to go via red links. Or I want you to avoid the blue links. Or I want you to go via this IP address. Or I want you to avoid this IP address. Same for SRLG, same for IGP administrative tags. So all of this is supported in this dynamic path where you express what you want to achieve. It's always an optimization target and some constraints. So what are the use cases for this? The low latency application here. So I'm at 1, I want to go to 3. I say, I want you to minimize the TE metric, and that's it. If I just want to get the low latency path, you configure the router this way. If I want to do plane affinity, I color all my links of the plane 1 with an affinity that is plane 1. And on 1, for the policy here, which should go the plane 2 traffic, I say, I want you to minimize on the IGP metric, and I want you to exclude the affinity, which is plane 2. And so, I'm sorry, so this is plane 2 is the blue, and by avoiding the plane 2, I want to restrict my traffic to the plane 1, which is the orange links here. And so, faced with this objective, the router number 1 will use its SRTE algorithm and implementation to compute, and he will find that the outcome is 16,014, which leads him to here, and then 16,003. Note again, we maximize ECMP. Always, we try to have the smallest seat list in order to get less labels to push and more ECMP. What if I want to do service disjointness? I'm at 1, I need to go to 7, I have 2 pseudo wires, each pseudo wire needs to be disjoint from each other. I build 2 policies, they both minimize on the IGP metric, but then this keyword is basically saying these 2 policies must be disjoint from each other on a node basis. They cannot share any node. Faced with these targets, the router compute immediately 2 disjoint paths and express them as SID, minimizing the SID list, maximizing the ECMP. The green path will be 16,002, then take this link, then there, and the blue path will be like this, in 2 labels. Okay? And once again, every time the topology changes, the router recomputes. Okay? That's dynamic, that's real-time update. So you have multiple, it depends what you, so the question is, will it load share? You could have a use case like this, but I know that use case for pseudo wires where typically you connect it, for example, to some TDM services, and you are trying to do a TDM migration to IP, and you're basically duplicating the traffic over 2 pseudo wires to do 1 + 1. That's the use case that I had to support, and I designed this for that use case. But you could use it for other applications, obviously. Okay, now I've explained it, the implementation, the capability to compute, this dynamic path. Now I'm going to...
Just a rough question. You say that the router needs to recalculate every time that, for example, one node disappears?
He must, and he will.
Okay, and there is no risk of flopping because the whole calculation will flop with the router or with the...
It's like everything. So it's a good question. What is the performance of this? So this is why we research so much. This is why we had this paper at SIGCOMM 2015. This is why it's a very famous conference with a rejection rate very high. We were accepted to that conference because the work scientifically has been very solid. So behind your question is the algorithm needs to be well thought in order to take less time to compute. Because indeed, if the network churns, you'll have to recompute a lot. And then the solution to this is always to reuse the past. ISIS, OSPF were faced with the same problem. And so what is the fail-safe technique? If the network churns so much that it's no longer the point to compute because you actually need to slow down, is to use exponential backoff algorithms. And so it's the same technique because I was working on ISIS fast conversions before, so I reuse all the experience. But good question. But again, the importance to work on this, I would say, on the scientific work behind, which is finding the algorithms, like TI-LFA, that we explained it 2 years ago or 3 years ago. The algorithmic behind TI-LFA to compute this fast reroute path is really strong. I mean, if you do brute force on that problem, you cannot do it on a router. It doesn't scale. So the algorithm makes it work or not the implementation. Okay, now I want to automate this. How can you do this? You can do this for Lisp, but I'm going to explain this for BGP. I'm the ingress router, and I'm receiving BGP routes. These BGP routes, they have a next stop, so they tell me where I want to go. If these BGP routes are colored with a color community, and I know that the color green means low latency, that's it. On demand, I receive the BGP route to the next stop, San Francisco, color green. I just need to know that green means low latency. On demand, I create the SRTE policy that minimizes the latency to San Francisco. I compute it. I allocate a binding seat to it. I install in the data plane. I say to BGP, this is the binding seat, and BGP installs the BGP route on the binding seat. Obvious. Obvious. And that's basically what we do. So this is the example I'm going to use. I'm going to receive a BGP route from 4, I am 1, and I have 2 paths. I have the IGP shortest path in orange, which is the high bandwidth, and I have the TE minimized metric path, which is the low latency. The premium VPN, they want to go green, low latency. The basic VPN, they want to go orange, high bandwidth. How does it go? The CE sends me a VPN route, 20/8. I recognize it as one who pays for premium. I tag it with the orange, the green color. And so I send the route to the route reflector with the green color. The route reflector sends it to 1. I receive it, and I see, oh, green color. The only thing I need to know is to map green to low latency. And then I do what I said before. As a BGP process at 1, I say to my TE process, my SRTE process, hey, I need a policy to 4, minimize on TE metric. He computes, he finds the label stack, he allocates a binding seed to the policy, he installs it in the data plane, and it comes back to me, the BGP process, to say, your handle is the binding seed, let's say 1,000. And me, I install my 20/8 on that binding seed. So that's the template. That's the only thing you need at the PE1. It is basically mapping the color to an optimization template. It's simply saying green means minimize on TE. And this template, you need 3 or 4, so you can minimize on latency, you could do plain disjointness, you could do service disjointness. You'll have maybe 3 or 4 templates, and they are all the same everywhere, so very easy to maintain. And so again, I insist on this because it's really the trick, is that the BGP route is installed in the forwarding table, not on 4. It is installed on the binding seed of the policy. And that's the trick to have automated steering. Automated policy generation, automated steering. So what is the gain? In the first time, I think, we have SLA-aware BGP services. We have SLA-aware Lisp services, because we can do this for Lisp-based services as well. There's absolutely no a priori full mesh of SR policy configuration. It's really nice, because if I have 100 of PE and I have 4 colors, in the old time, you would have had to maintain 400 tunnels and then steer things onto them. Now, by default, you have nothing. You receive BGP routes, and then you build them on demand for those you really want. So it scales much better, because at any point in time, a PE might only have some BGP traffic to other PEs for some colors. And you have no longer any complex steering. It's automated via the binding seed. OK, we've done intra-domain. Now I'm going to go inter-domain. And because I have only 45 minutes, for TE, I need to give you the key aspect of it. What is XTC? XTC is simply my XR code, so the code that I showed you before, that I virtualize and run on a server. And hop, I have a controller. It's exactly the same code. Same algorithm, same database, same everything, okay? So that XTC, you could run it on a physical router as well, or on a virtualized server on x86. It's the same. He has this building block to compute, which is the same algorithm, and then he has this multi-domain database that he feeds from multiple domains. And so he's able to see everything. And he's going to compute in the same way, but on a bigger database. The only thing that I need to do to tell my XR code that is a PCE server that is going to help the others, because the others don't have the same database, they only have the database with the local domain, is to tell him, you need to help the other. And this is what it means. You must be a PCE. So a PCE means you are a helper for the others. And you are going to help the others on this IP address. And all the routers here, they only have the local domain view. They have the same algorithm, but they have less topology. So when they will need to compute an inter-domain path, they will send a PSEP request to him on that IP address to say, hey, help me. I need a low latency path there, but me, I'm blind. I don't see beyond my domain. He computes and he will answer to the router. This is stateful. So when, for example, my SD1 controller, my BGP controller, my Lisp manager sends me a VPN route, and I learn here that the next stop is there, but I don't know how to reach him, I'm going to, on demand, send a PSAP request to him and say, where is it? And he's going to compute and tell me how to go. It's very important. This slide is this word that is keyed. This process here is stateful. It's not like you ask me, I tell you, I forget, because that would be useless. You ask me, I tell you, I remain accountable for you. So if the multi-domain topology change, I will recompute and inform you so that you can always be up to date. Without this, it's useless, obviously, because then it would be blind to what is happening to other domains. It is HA. These XTCs, you should think of them in pairs. And here we simply reuse PSAP high availability technology that has been defined in the past, and so we're simply reusing this. This, again, I try to give you the key points. The XTC controller is not a God box, because we don't want this. It's not like this box in the middle that if you lose it, you lose everything. I designed it to be like rod reflectors. So they are distributed per service, per geography. So you should think that you may have, for example, if you are a European network and you have a point of presence in Amsterdam and for the Netherlands, but you have 2 XTCs in Netherlands for the VPN service. And maybe you'll have 2 XTCs in the Netherlands for the voice over IP service or another important service. So it's per geography, per service. So it's completely distributed. You have no one God box that could fail and impact the availability of all your service. What?
And they will be able to talk to each other in the case you are going out of the region?
If one day we need it, yes. But currently, this is not the way I design it, because I think it's not needed with the design and deployments I see. So what I have now is that, if you wish, I have 2 XTCs that help this data center. And so when this guy asked me, hey, how can I go there? He asked me, and I am authoritative, because these XTCs, they have all the topologies. So they are independent. This is why I said before, there's no, this is like rod reflectors. They are all having enough information to compute independently for the client. These 2 are responsible of these clients, and they are completely independent of anything else, because they learn the topology of this, the topology of this, the topology of this, and the topology of this. In the future, a couple of years from now, if we have, let's say, new use case, new scale, etc., it's clear that we could have mechanism where, like the DNS, we have recursive computation. And this, I think, over time may happen. It's how to say, expected in the architecture. But in the beginning, we don't need it.
You have said that XTC has the full visibility of the architecture. So, yeah, for inter-domain. But inter-domain under the same administration control, right?
Yes, indeed. But because, so the question is, inter-domain under the same administrative control. I am a very pragmatic person. If you tell me how you're going to do traffic engineering over the internet with a business model and someone who is going to pay for it, then we'll discuss, but me, I've never seen it. So there are so many use cases inter-domain in the same, think about very large mobile provider that span multiple countries, very large providers in US which are created into subdomains. The applicability for multi-domain under the same administrative control is huge. So me, I'm focusing on this. Okay, what are the use cases? First use case, service disjointness. In 2 ways. Multi-domain, this, I need my XTC to help, But furthermore, the two pseudo-wires are between different head ends and tail ends. So obviously, one is unable to compute this because he doesn't know where 6 is going to go. And 6 cannot compute because he doesn't know how 1 is going to go. So the way it goes is that 1 is configured with this, 6 is configured with this. Let's see what 1 is set. So I'm telling to 1, hey, you have a policy 1. You must go to 3 with the color 20, so green. You have one path, which is dynamic. I want you to compute. I want you to minimize on the IGP metric. You cannot compute it because it's going beyond you, so you need to ask the PC to help you, and that's the blue line. I want you to be disjoint on a node viewpoint with respect to a group 1. And I'm saying the same to this guy. To 6, I say, you want to go to 8, you want to minimize the IGP metric, it's dynamic, you cannot compute as the PCE, and you want to be disjoint from 1. So the PCEs, obviously it must be the same pair of PCE. So when they receive the request, they say, they want to be disjoint. And so they compute 2 disjoint paths, and they reply to each disjoint path. So in this problem, the XTC here would say to 1, you must take these 2 labels, and this will be the green path, and he will reply to this one, you need to take these 2 labels, and it will give you this path. And they are disjoint, while minimizing the number of labels and optimizing for more ECMP. But I can either do even better than this. I can also run inter-domain services without any inter-domain redistribution. I have ISS here, I have OSPF here, I have no redistribution. These islands are disconnected. I give a VPN route to him with a next stop that is free. On demand, he asks to the PC, that next stop is beyond me. Tell me how to go. And that's very powerful because it goes into inter-domain services where you can scale all your domains independently. They are completely isolated from others. There's no longer BGP redistribution. And you know very well that in the very large-scale deployment, if I have, let's say, 10,000, 20,000 of access nodes distributed between different 20 countries, each access node has very little communication with all the other access nodes. It might only communicate to maybe 10 other access nodes. So it's much better to discover this connectivity on demand than to push the connectivity to everybody. So we support it, and that's the demo that José is going to do. And that's obviously very successful from a design and deployment viewpoint, so that's why we were so busy not documenting enough, unfortunately, the T, but now it's documented.
Just one question. The first PCE, he knows only 1 and 2, and the second he knows 2 and 3.
No, this PCE is learned with the topology of this one, and he has a BGPLS session into the BGPLS route reflectors here. He learns both. I describe it, when I put it in yellow like this, it means this is my same piece of code, but fed with the topologies of the other ones, because it's the same code. So the difference between this and this, from a code viewpoint and running viewpoint, is the same. The only thing is that E only has the topology of this, and he has this topology and this topology. Now, next point. If I receive IM1, there is no inter-domain routing. I don't know where 3 is, but I receive a VPN route, a Lisp route, that tells me this pseudo-wire endpoint is 3, and you must have low latency to it. But I am blind in 2 ways. I don't know where 3 is. It's beyond me, and I need to go at low latency. So for these 2 reasons, I on demand, when I am programmed with the service, either via NSO or BGP or Lisp, when I'm programmed with it, I see I need help. And I ask the PC, where is 3 low latency? He computes, he's stateful, he tells me the answer, he tells me use this label and then that label. This label gets me to here, and then this label becomes visible, and that works because this label is a label from this domain. So from 2 to 3, it will work. So he's right. But furthermore, he's stateful, and he's watching the topology of the two domains. And if the domain change, he recompute and give to one the updated path. So now it's the automation, but I think you got it. So I'm going to skip it. And that's the only thing you need to do. So on a router, you imagine a little access node in one of these 20 countries of a very big international provider, and you might need to get connected for pseudo-wires with 20,000 of other access devices. That's the only thing he needs. It's basically to say, if he's receiving a next stop he doesn't know, and with a color community that is low latency, he must ask help to the PCE, and the color green, low latency, means that it must minimize on the T metric. That's the only thing he needs to know. So when he receives the service route, he says, next stop I don't know, color green, I say to PC. PC computes, and it tells me. So this is also why when we give a shorter talk, I say segment routing is a hybrid architecture, distributed intelligence, centralized intelligence. The hybrid comes from this. Because I have intelligence on the router. I could compute if it would be in my domain. And I am able to generate, to trigger all the automated policy and steering. It's just that it's beyond me. And so I need to ask the controller. But it's a hybrid. It's not completely centralized because it's not the controller who tells me what I need to do. It's me who asks him. And that makes a huge difference, in my opinion. It's much easier to look at it like this. Why? Because then the master is the service. It's your service. It's me as an access device. I'm a slave and I wait to receive a service. And when I receive the service, then I trigger all the process. It's not the underlay that is the master. It's the service who is the master. Conclusion. I hope that you can see it's simple. Compared to all what we've seen over the last 20 years, I think that we have taken it from scratch, completely new process, new CLI, new thinking process. It is simple, entirely automated, and scalable. The scalability because of SR, we have no state in the core, we have the state in the packet header, but furthermore, we have eliminated configuration at the edge. Finished the full mesh of tunnel. This is through on-demand generation of policies based on your BGP colors, your Lisp colors, and then on-demand steering on these policies. Same piece of code can be run virtualized and give you the multi-domain applicability. And your question?
I use the mechanism of PHP. The mechanism of PHP electric hopping and the layer to suppress.
Yes. So the question is, do we use PHP? The answer is yes. I did not go through this because it's an advanced talk, so we always use PHP when we apply segment routing to MPLS because it's much better. Okay.